So someone has asked that is this session in continuation with the 3 to 5 session held today earlier? Yeah, so actually how this is going about is that in this course we have 2 tiers, right? Ativ is taking a session from 3 to 5 and I will be taking this session from 5 to 7. There may be some overlap between the content because it is based upon the lectures whatever was posted last week, right? But I think that you can attend both the sessions, or you may, it is up to you, or because the recorded lectures will anyhow be posted on YouTube, so you can refer later also. It is as per your convenience. So it's 5. So welcome everyone. Uh, let's wait for a couple of more minutes because I think the previous session has just ended. Then you can start. Okay. In the meantime, let me introduce myself. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar. So I will be okay. So I haven't said anything, Bhagmita. So I haven't said anything yet. So I was just introducing myself. So welcome everyone. This is NOC EE-91 NPTEL tutorial course on semiconductor devices and circuits. So what we do basically is that whatever the lecture has been posted in last week, for example, this will be based upon week 1 lecture content, whatever Professor Sanjeev has posted in the course web page. So we formulate some of the problems, numerical problems mainly, to help you solve the assignments, whatever you are assigned for the which will be due by 9th August or 8th August, right? So it will follow this trend only. So I am one of the TS for this course. So I will be going live every Sunday 5 to 7. Okay. So welcome again. So some basic prerequisites for this session would be that I will expect that you have at least attended the lectures, whatever has been posted on the course web page, and also you have attempted the assignments by yourself once. Then you can discuss the issues you are facing, right? With the similar problems which I am showing or solving in this session, you can ask your doubt in that regard. But if you do not at least attempt the problems, then it will be difficult for you to grasp all the concepts. Okay. And also to maintain some decorum, please keep your microphones muted all the time. This is a Zoom platform, so you can use your raise hand options if you have any doubt. Also, I will go pretty slow for the first lecture so that you can ask your doubts, and I will give you some time after each topic or each problem I discuss. Then at the near the end of second hour, I will give you some time of around 5 to 10 minutes to ask your general query, right? And please keep a scientific calculator nearby to you so that you can do the calculations along with me. Okay. So just a basic question. How do you guys want to do this session? You want to make it interactive, or should I just solve the problems? So whatever is convenient to, I can follow that. So any one of you can type in the chat box that you wanting to make interactive, so that, see, there is no grade points or nothing on this. It is just to clear your concepts, right? So if I ask you, suppose whatever the basic stuffs, if you do not know, that is very fine. I can explain those things also again. Okay. So how do you want it to go? Anyone can comment on the chat box and or unmute at this point so that we can be on the same page. Okay, solve the questions if necessary. Oh, Neeraj, what I interactive? Okay, so let me do the hybrid thing then. I will ask some questions. If you can answer, just answer. Or if you do not understand the question, then also it is fine to ask whatever I am, or tell me to repeat the things, right? So anyway, let's begin. And by the way, the link of the recorded lectures will be, if not shared already, will be shared to you via a Google spreadsheet. Okay. So there will be the YouTube links where these lectures will be posted for record and also for your later referral. So this is week 1. Let's begin. So the first problem is pretty simple, right? It is asked that the wave function of the particle must be normalizable because there are 4 options given. The particle's momentum must be conserved. The particle cannot exist at 2 places at the same time, or the particle must exist somewhere in the space, and all the charge is conserved. So first question would be that what are we talking about? What is this wave function, right? So can anyone volunteer to tell what is this wave function? What do you understand by this wave function? You can unmute. Yeah.
Sir, does it describe the probability of finding the electron?
No, actually not, right. See, just let me tell you. Wave function. First of all, what is this wave we are talking about? All measurable parameters about the wave particle. Yeah, that is fine. That wave function shows me all the required information about the wave, right? But what wave we are talking about, right? You must remember that it is mentioned that wave function of the particle, right? Wave function of the particle must be normalizable. So wave function of the particle, first thing to note that it is an mathematical abstract only. Okay. So what happened that you know that in when we go to the smaller dimensions or in quantum realm, the energy and charges, everything starts to become quantized. Charge is anyhow quantized in classical mechanics also, but your energy starts to get quantized, right? Because in narrow confinements you have certain energy levels which the particle can take only. So that's how the name quantum mechanics came in the first place. Or mathematical function of space and time and contains all the measurable parameters of the electron. Not only for the electron, yeah, it can be of any quantum, any small particles, right? So this was introduced by Schrödinger in 1926, right? And throughout this lecture, you will see that at some point I will explain how this Schrödinger equation has come about, right? From what concepts it has evolved. So basically, you note that it was based upon your Planck's hypothesis that energy is quantized E equal to h nu, and your de Broglie, or you may say de Broglie's relation, right? This is your E equals to h nu, and this is your. Can anyone say what is this de Broglie's relation? Is nothing but your linear momentum, or not linear momentum, actually be careful about it. It is your crystal momentum, right? This P is crystal momentum. This is h by lambda, right? So this is basically a wave function. You say that you can think of this wave function as some wave amplitude, right? Some plane wave amplitude. It is not exact expression, but you can think of for the beginning point of view. So it is explained this wave function is generally expressed in terms of this psi, right? This psi quantity. Role of the theory of this training. Yeah, I think these questions you I will, okay, if you have these questions till the end of this lecture, you can ask me during the end, right? I will answer this at the end. So this wave function is basically explained by expressed by this psi, right? It is a Function of space and time, as someone has already said, it was correctly pointed out that it is a function of space and time. So the nature is that it can be complex. Yeah. So by definition, if it is complex, then that means it can be real also, right? Because real numbers are nothing but one of the abstraction of the complex number, real or complex. Fine. So what does this psi do? As someone has told earlier that it shows the probability, right? So it does not actually tells you about the probability. The probability, which was probability density, or I would say, is given by this complex conjugate of psi multiplied by this the wave function psi, right? This gives you the probability density of finding a particle in some volume, say some volume dv, right? I am considering any arbitrary dimensions of space. It can be 3D, 2D, and 1D also. Okay. So you know that the particle with which this wave function is associated is needed to be present at least somewhere in the space, right? So you see that the probability would be, this is the probability density, mind it, this is the probability density, and this when multiplied with the volume, it gives you the probability of finding that electron in that dv. Okay. And when you integrate it over all volume, let me just put it in this way. This or this symbol you are familiar, right? This is the for all symbol. For all volume, this you can write also. In 3D, it will be a triple integration. dv has to be 1, right? Because we know that from probability theory, right? The total probability of the universe has to be 1. So the probability of finding that particle in the entire universe or in the entire space has to be there. There has to be 1, right? So this integration is also known as normalization integral, right? So from this discussion, the question is answered that the particle must exist somewhere in the space. So that is given by this normalizable property of the wave function, right? So till this it is fine. So let's now dwell into the other options. What does it uh, prohibiting us that the other options will not be right? Okay. So first option, let's go to the first option. The particle momentum must be conserved. So what does this momentum conservation means? Any of you can tell me if you have ever come across that, where these laws of conservation of momentum, charge, energy comes about, from which fundamental principles of nature these things come about. Have you ever thought of, because we are always told from our childhood that energies must be conserved, right? But why? Again, momentum must be conserved, but why? Have you ever thought about it? Can anyone tell me?
So is it to maintain the balance in the universe?
Yeah, that is actually a very good answer, and it is a very broader sense. I want you to be more specific and more scientific, right? What do you mean by the balance of the universe, right? For let me tell you that, uh, okay, for example, this momentum conservation, right? This momentum conservation, let me just write it down. And now the question may come, what momentum I am talking about? I am talking about the linear momentum, right? Not the angular momentum. The angular momentum is also conserved is a conserved quantity, fine. So this momentum conservation comes from the fact that, suppose this is your entire universe, right? And this is the space. So at this point and at this point, the laws of physics must be same. What does that mean? This means that the homogeneity of space from this concept, actually through quantum mechanics only, you can derive that momentums can be conserved. Okay, but this is not directly attributable to this integration. Okay, so that's how your momentum gets conserved, because you do not have a preferred point of space where the physics will be like laws of physics will be valid, and here these other laws of physics will be valid. Laws of physics will be valid in every point of space equally. That is called the homogeneity of space. From that, this conservation of momentum is there, right? Similarly, the particle cannot. Similarly, the let me go to the last one first. The conservation of charges. Conservation of charges you can explain from the fact that conservation of
Recording in progress.
yeah. Sorry, am I audible? Yeah, I got disconnected somehow. Hello. Yeah, yeah, fine. Okay. So conserve. I was talking about the conservation of charges, right? Conservation of charges comes from the fact that you see, you whenever you write this kind of wave function, right? It is basically it needs to have some phase. Okay. This phase is basically arbitrary. It can be anything. From that arbitrary nature of this space, this phase of the wave function, you can actually derive the conservation of charges. So basically, my point of saying this all is that there is no preference in the nature or the universe, right? From that basic fundamental concept, the things that conservation of momentum, charges, and energies, all these things come about. Okay. So for this question, if these things, right, momentum, if I will discuss about the operators, then we will discuss more about the momentums. Okay. And the particle cannot exist at two places at the same time. That is not true, right? We know that a particle, yeah, that is another thing is observability, that how you measure that one particle, that is from your Heisenberg's uncertainty principle, right? From where you know that if you can measure that your position perfectly, then you cannot measure the momentum perfectly, right? So this kind of things may be there, but a particle cannot be present at two exact points, and that is not from the, you cannot directly tell from this normalization integral, right? So that's why that option is also not right. So your C will be the right option. Okay. So moving on to the next question. By the way, for this these concepts, if you want to read further, you can refer this book, right? Griffith's electrodynamics. Okay, if you want to get more concept regarding this topic. So let's move on to the next problem. It is mentioned that which of the following is not a valid quantum mechanical wave function. So can you tell me what are the properties of this psi? Any one of you?
So it is continuous.
Okay, and also only psi, continuity of psi will be sufficient, or
So
uh,
derivative should also be continuous.
derivative should also be continuous, right? And also, so your psi and
Should be a solution of Schrödinger's equation.
right. Psi is the solution of Schrödinger equation, right? So
And
these
it should be
things continuous, and also it should be single
normalizable.
valued. Yeah, right. Single valued. It should be normalizable. And another thing we don't generally talk about is that psi should be well behaved function, right? Have you heard of this thing? Well behaved. Any one of you, have you heard of this point also about the property of psi? No, right? Okay. So well behaved means, what do I mean? That it
It
should
does
not,
not suit up.
sorry?
It does not suit up.
Yeah, right. It does not suit up, or it does not blow up, right? Like delta function. Yeah, you are absolutely right. Well behaved means it should not have any singularity, right? Any singularity. Okay. So these are the properties of this psi. So from that very point, you can easily tell from this four plots that which one should be psi, right? Uh, because first thing that your psi should be continuous. Okay. So if your psi should be continuous, this function is continuous, this one is also continuous, this one is also continuous. But do you think this function is continuous? This is not continuous, right? Because if you take the limit from left hand side of 0 minus, limit from 0 minus 2, and also from limit from 0 plus, you will see that this does not converge to a same point, right? So this is not continuous. At x equal to 0, your psi x have multiple values. So it violates the condition of the property of this wave function, right? So this one cannot be, is not a valid quantum mechanical wave function. So your fourth one is not a valid quantum mechanical wave function, and it relates to the property of psi, that psi should be continuous and psi should be single valued, right? So this property is, it is getting violated. So it will not, the fourth one is not a valid wave function, right? So let's move on to the next problem. The ratio of two, the ratio of maximum and minimum intensities in an interference pattern is 25:1. Then the ratio of the amplitude of the two interfering waves will be. So how do we do that? So let's assume that we have two waves. Okay, I will go this problem mathematically first. So let's say it is a sine omega t. Okay, a1 sine omega t, let's say. And another way will be a2 sine omega t with, let's say, some phase difference will be there. Okay, so what is the amplitude? Please unmute and tell me what is the amplitude of these waves and what are the intensities.
A1
Anyone?
and A2 are the amplitudes.
And intensities, what about the intensities? So what do we mean by intensity is that if I take it I1, it should be proportional to A1 square. Okay, A2 square. Okay, so for the time being, let me take the proportionality constant as 1. So I can, without loss of generality, I can just write it as this for the ease of our calculation. Okay, so when the wave superimpose, what will be my y? Y will be nothing but superposition means, or interfere, they interfere means we just sum them up. Okay, so y1 plus y2 will give me a1 sine omega t plus a2 sine omega t plus some phase difference between them. Okay, that phase actually determines where the maxima and minima of my peaks of the interfering pattern will be there, right? This is from the class 2 plus 2 level physics. Okay, so if you can break this, so you will see that it will be a2 sine omega t cos phi plus a2 cos omega t sine phi. Fine. So now if you can take this common of sine omega t, a2 cos phi, a2 sine phi, and cos omega t. Okay. So now if your interfered wave, let's say the total thing is a sine omega t plus theta, of the total interfered wave, right? The superposition of two waves. Then you can again break this cos theta. I am taking a different angle, okay, because it is a superimposed wave. I am taking the equivalent form, mathematical form of that. Cos omega t sin theta. So now if we compare these two equations, so we can write that your a cos theta is nothing but a1 plus a2 cos phi, and again your a sin theta would be your a2 sin phi, right? So if I want to get a square, because I want to get the intensity of the total wave, right? So I can write this a square sin square theta plus a square cos square theta. So from that I can see that I can write a1 plus a2 cos phi whole square plus a2 sin phi whole square. Okay, so if we just solve it, so you will find out this kind of expression, right? So let's say this is my I, total intensity of the wave. Okay, so what will be my I max from this? This is a square term, right? So it will anyhow be positive. So this will be my some constant multiplier, and this is cos theta. So what is the maximum value of cos theta? Maximum value of cos theta is 1, right? So your a1 square plus a2 square plus 2a1 a2, and your this phi would be 0 degree, 2 pi, 4 pi. Okay, so in these cases it will be my cos phi would be 1, and then you can write simply that it is a1 plus a2 whole square. Similarly, you can easily see that the minimum value of cos phi is -1. So by default that it will be a1 minus a2 whole square. Okay, so I have been mentioned that the ratio of maximum and minimum intensities of the interference pattern are 25:1. Okay, so I max over I min is 25 by 1, or your a1 plus a2 square by a1 minus a2 square is 25 is 2 over 1. So your a1 plus a2, a1 minus a2 is nothing but 5. So you can simply solve a1 over a2 at what it will be, 5 plus 1 over 5 minus 1, right? So it will be your 6 over 4 or 1.5, right? So your correct answer would be B, right? 1.5. Did you follow it? It is pretty easy actually. If you have any question, you can ask. Okay, so let's move on to the next problem. Yeah, this is a good problem. Okay, so it is mentioned that in electron beam lithography, patterns are exposed with electrons, right? The small wavelength of electrons helps to achieve a small feature size in order of nanometer. Assume an electron gun has this amount of energy. What is the wavelength of the electron? Okay, neglect the relativistic effect. So first thing, can anyone tell me what do we mean by lithography? It has nothing to do with the solving of the problem, okay, but it is better to know what the question is asking. Can anyone tell me what is lithography? Oh, no singularity means okay, I just need to go back. No singularity means, you know, singularity you see in your control system that in your control system you have this your some transfer function, you write it in terms of h of s, let's say some s plus z1, s plus z2, some poles and some zeros and then some poles, right? So what happens to at the pole locations? At pole locations, the hs becomes infinity, right? The modulus of hs becomes infinity. So at any point where the amplitude of the function becomes infinity, that then that we call up, it is shooting up. Shooting means shooting up or blowing up, like just a delta function. Okay, so this kind of thing we call a singular function. At this point there is a singularity. Okay, I missed your this point. Okay, so yeah, I was talking about lithography. By the way, lithography, you have you heard of, haven't you heard of photolithography and all? I think people are saying that no idea.
So,
Yeah.
is it something related to the manufacturing of semiconductor where we like dope the both?
Yeah, right. It is related to the manufacturing of the semiconductors. But how does it? How do you do that? Suppose you have idea of p-type and n-type semiconductors.
Yes, sir.
Okay. So do you know how that those p-type and n-type semiconductors are actually made in practice? Suppose you have a silicon wafer. Okay. So you want to make a pocket of this. Yeah, right, doping, right? But how that doping is done physically? So this pocket of say n-type you want to make it. Okay. And this is a, say it is a p-type silicon. Okay, you want to make a p-n junction like this. Okay, so how do you do that? First you take your litho, or means your stone lithography, right? Litho means stone. Stone here we refer to silicon. First you take your silicon wafer, then you do your diffusion or ion implants, right? Suppose I want to make it a p-type, so I need to make it, dope it with some group 3 element, say boron, right? So diffusion or ion implant I will do. For that I need to have some electron gun at this place which shoots electrons, sorry, which shoots your this ions of boron atom, and it will get diffused in your silicon, it becomes p-type, right? Then suppose you want to make a very small window, say this is your 100 nanometer. Okay, 100 nanometer, for this 100 nanometer length and 100 nanometer width you want to make a n-type doping, but you do not want it other way, other sides or around it, right? So how do you do that? Suppose it is your top view, right? So you want to make a n-type doping here, this is your 100 and this is your 100 nanometer. Okay, so you, what you do, you have actually a kind of, you know, mask, what we call, where you will have this, everything is covered except this one hole of this 100 by 100 nanometer, and then you drop your electron gun on top of it, or whatever your this ions and all, and then you start to dope at this place n type on top of that p type, right? So this is done actually for multiple steps. When you go, when you will read about MOSFETs and all, this kind of photolithography, why it is called? Because some, if you want to put some metal layer or some oxide layer on top of these elements, you need to have some kind of photoresistive materials. You will read about these things later in your courses. So for the time being, lithography means some patterning on stone or some patterning on silicon, right? Like your doping and all. So for that, in many places, in electron beam lithography is one kind of thing. for that your this electrons, high energy electrons are implanted, right? Okay, so that is what we mean by lithography. So just let me note. Okay, so that is what you mean by lithography. So now you see one thing, that in if you want to make a region of 100 or over 100 nanometer, right? So there will be more than one electrons at least, right? So multiple electrons should be there. So suppose your electron wavelength is such that one electron wavelength covers the entire 100 nanometer region, right? Then it will serve no purpose, right? That means in that region you will have one electron. So you need very high energy of electrons, so that the wavelength associated with that electron is so small that in nanometer printing you can do. Okay, so that is what is mentioned there, that the small wavelength of electrons helps to achieve small feature size of nanometer scale. Okay, that means your electron wavelengths will be much lower than your nanometer length, okay, to accommodate multiple electrons in that nanometer region. So now what are they asking? That they are telling 50 kilo electron volt is the total energy associated with the electron gun for one electron. Okay, so can you write 50 kilo electron volt in joules? Joules is also in unit of energy. Can anyone unmute and tell me how to write the kilo electron volt into joules?
1.6 into 10 to the power minus 19 will multiply.
And also will multiply 10 raised to 3, right?
Yes.
For this kilo part. Yeah, you are absolutely right. This is joules. Okay. So now what are they asking? They are asking us to find out what is the wavelength associated with it. So how do you go about that? Electron is not a relativistic particle. That means it is not photon, right? So you cannot use the expression E equals to h nu at this place. Okay, E equals to h nu is the energy of a photon. For electron, from a electron gun, it has only kinetic energy, right? So what is the kinetic energy of any particle of mass m and velocity v?
Half mv square.
So it is your half mv square, right? Will be this energy. Then can I write it in this form? Mv square over m. That means your E would be p square by 2m. P is your momentum, okay? Where P is equal to mv. And also the de Broglie relation or the de Broglie relation have its validity for any large or small dimension of element of particle. Okay, so we have de Broglie relation. And what is my de Broglie relation? P equals to h over lambda, right? So you see that you have these two relation. In one case, E equals to p square by 2m, and if we put p equal to h square by lambda square, then you have this relation. Okay, so you want to find out lambda, right? So your lambda square would be h square by 2m e. Fine. So your lambda will be nothing but h over root over 2m e. Okay, you know h is given already in the question. So what is h? And also make sure you note the units very carefully. Okay, 6.626 into 10 raised to minus 34 joule second. And what is your mass of electron? Me is 9.109 into 10 raised to minus 31 kilogram. Okay, so you have your m, you have your h, and you have your e also, right? E we have found out 50 into 10 raised to 3 into 1.602 into 10 raised to minus 19 joules. Okay, I am doing everything in MKS or SI units. Okay, so from this equation you can find out your lambda. Just plug in these values in this. So if you plug in these values and see your lambda will come out to be around 5.48 10 raised to minus 12 meters. Okay, so the answers are given in nanometers. So what do? You just break it. Okay, 10 raised to minus 9 meter. This is your nanometer. Okay, so 5 point, let's say it is 5 into 10 raised to minus 3 nanometer. So 0.0055 nanometer. Okay, so this will be your answer. Okay, you see, how do I find out this? Did you follow the steps?
Yes, sir.
So if you have followed the steps, you see I have neglected one particular part of the question. Okay, that is that neglect the relativistic effect. In which place I have used that? Can anyone tell me?
Sir, we have assumed it as elastic collision, wherein the momentum value remains unchanged.
Right. Can you introspect further? You are on the right track. By the way, what do you mean by relativistic?
Sir, there is no effect of hitting the electrons in the
No, relativity,
experimental.
relativity. You have heard about Einstein's theory of relativity?
Yes, sir. As we move at a speed relative to the light, there
Right.
will be reduction in mass.
There will be reduction in mass or increase in mass.
Sorry, reduction in length. That is what we increase in mass.
Increase in mass, right?
Yes, sir.
So yeah, you are Srihari, right? Srihari, you are absolutely right. That here what happens is that, let me just explain, because these things are very important and salient feature in the question, which you should note always. Okay. So what is happening is that I have find out my P. Okay, for 50 kilo electron volt energy, I have found out my MV to be, did I find out? No, I didn't find out, right? Okay, so let me just find out. P square equals to 2me. So 2 into 9.1 into 10 raised to minus 31 into 50 into 10 raised to 3 into your 1.6 into 10 raised to minus 19. Okay, and this, there is m, this is p square. So if you find out your v from here, because m already you have, this is your m, so you will find out it will come out to be around 1.32 into 10 raised to 8 meter per second. Okay, so the velocity of electron is, from this you can find out your velocity of electron. For this energy, velocity of electron would be 1.32 into 10 raised to 8 meter per second. Can anyone tell me whether should I consider this as relativistic or not? Because the speed of my light is 3 into
We
approximately
have
is
to
equal
consider,
to
sir.
3.9, right? We have to consider. But what happens actually, that in question it is mentioned you should not consider this relativistic effect. So that's why what you can do, you can assume the mass of electron as the rest mass of electron. That is your 9.1 into 10 to the power minus 31 kilogram. Okay. So now for suppose I increase this energy. Okay. I increase this energy. Say I make it 200 kilo electron volt. Then if you calculate, you will see that your VE starts to become or almost double, 2.64 into 10 raised to 8 meter per second. Okay, so this is very much nearby, near to that velocity of light. So it is almost a relativistic, electron has become a relativistic particle at that high energy. So at that case, you cannot use this equal to this relation. Okay, then you have to incorporate something we call M effective rest mass of electron into some new let me not use this, let me call it some L. Okay, Lorentz factor, and you know that L is nothing but root over 1 minus v square by c square. C is your speed of light and v is your velocity of electron. Okay, so now for example, your v is 1.32 into 10 raised to 8 and your c is 3 into 10 raised to 8 meter per second. So your M effective becomes, if you can calculate it quickly, that 1.32 divided by 3 whole square, 1 minus answer 1 over that 1.32 over 3 square, 1 minus answer root over answer. So right. So your M effective will become around 1.11 into M naught. Okay. And now for the, this is for the 50 kilo electron volt case. Now for 200 kilo electron volt case, what will happen? My V was 2.64 into 10 raised to 8 meter per second. Okay. For that case, if you calculate your M effective, it will come out to be 2.64 over 3. Yes, answer. It will become almost 2.1 into M0. Okay. Just cross check this calculation. So you see that as your energy of the electron gun increases, your mass, whatever you are considering in this equation, right, this M starts to deviate from the rest mass of the electron that was given in the question. So that you need to start to calculate if this statement is not mentioned. So this is a very important statement, that whether you should consider the relativistic effects or not. So keep this in mind. Okay, in exams also, if it is not mentioned that you should not consider the relativistic effect and something like that, you should always check the velocity of the electron, and you should check that how close it is to the speed of light. And if you see it is quite pretty close, and I would say more than, for a thumb rule, you can just take that uh, greater than equal to 100 kilo electron volt electron guns, you should consider this relativistic effect. Okay, then you need to calculate this mass, and this you will put into this equation. Okay, please tell me if you have any doubt now regarding this last part, because I know the earlier part is pretty simple and you can do. But if in exam it is not mentioned, then you need to calculate this mass using the Lorentz factor. Okay. So anyway, I will share these slides, the solutions, you can refer back. This is called Lorentz factor. This is from the special theory of relativity. Okay. As Srihari has pointed out. Okay. So let's move to the next problem. An electron in an infinite one-dimensional potential well jumps from the energy n equal to 4 level to the ground state energy level, and in doing so it emits a photon of wavelength 20.9 nanometer. What is the width of the well? Okay, first let me ask you one thing. In your from your 7th or 8th standard till now, where did you first heard of that quantization of energy? That energy has to have some certain values only. In which theorem or which postulates you have heard this? Can anyone unmute and tell me?
So is it Bohr theory?
Yeah, right. See, you are right, absolutely. That in Bohr's postulates, you have heard, right, that around the nucleus, the electrons can move at a certain distance only with a certain energy level, right? From that leads to the quantization of energy. Okay. Now that Bohr theorem is not completely valid. Okay, that is all. That's why it is called postulates. And by the way, what happens from when an electron jumps from one energy level to another energy level, from a higher energy level to lower energy level?
It loses energy.
In what form?
Light.
In the form of light.
Light.
Is light the most
Light and
convenient
heat.
form?
Light and
Right.
heat.
Yeah. Heat is the most convenient form. Okay. Light is very special case, but heat is the, that's what I wanted to know actually, whether you know this stuff or not. That whenever from a high energy level to a low energy level, some electron jumps, because why does it jump? Why cannot it gradually fall? Because from one energy level to another energy level, there is some forbidden region. Okay. So there the electron cannot be there. That is what we mean by quantization. Means either you can be at 1 or you can be at 2. You cannot be at 1.5. For example, I am just telling. So when a electron goes down from level 2 to level 1, that means high energy to low energy, it loses energy. Generally, it loses in forms of heat, but it also loses it in forms of light also. So understanding this question is not difficult. Okay. First, you need to read the question carefully and understand what does it tell. That in an infinite potential well, so if by the way, when we draw this kind of well, can you tell me what is the x-axis and y-axis?
X-axis is the distance.
Fine. What is the y-axis?
Is the wave function.
No, no, no.
Potential.
Yeah, that is potential, right? This is your infinite potential. And let's say this is your x equal to 0 and this is x equal to L. Okay. So suppose, and why can't, and you have also heard about these things, right? That psi at this will be 0, psi at this place will be 0, but psi at this place will not be 0. Why do you think that psi of this will be 0?
The particle must be present inside the well.
Why?
No, because it is infinite, so the electron can't go to the other region outside the well.
Since outside the well there is an infinite potential present, no particle cannot achieve that. So the particle
Right.
must be present inside the well.
Yeah, fine. It is just simple analogy that if you are standing at the bottom of any well, then you see upwards. If you have infinite walls of the well, then you cannot go to the other side. Okay, it is as simple as that. So this is from, and how does psi be 0? Because your probability of finding that electron becomes 0, right, at these two regions. So your this quantity becomes 0, and you can refer from this that your psi can also be 0. Okay, so that's why we do that. Psi is 0, we consider psi 0 at the outside of the well. Okay, so okay, now tell me, how do I solve this kind of problem? First I need to write the Schrödinger equation, right? Is this the Schrödinger equation?
This is the energy balance equation from Schrödinger's equation.
Then what is the Schrödinger equation?
There are two forms, time dependent and time independent.
No, you can take any one of them. Isn't this AC, Schrödinger equation? This is actually Schrödinger equation, right? And whatever you have told is where I was coming about. That Schrödinger equation is nothing but energy balance or energy conservation. Okay. So this thing you should be very clear about. There is nothing, any difficult nature of this. Okay. Schrödinger equation. It is very simple once you understand this thing. By the way, let me write it in one dimensional, which is more conventional to you, convenient to you. Plus V of psi equal to E of psi. Okay. Now can you tell me what is this?
Kinetic energy.
No. Please look at it carefully. What part I am uh, highlighting?
Energy operator.
Energy operator, right? What is an operator, if I may ask you?
With which we can perform differentiation on the parameters.
No, actually you are quite close, but not exactly. By the way, this is your kinetic energy operator, this is your potential energy operator, and this is your total energy operator. Okay. So what are the operators? Let me ask another person. You may be knowing this stuff, but someone else which is joining, maybe this becomes very difficult to understand. Is anyone there who are getting these things difficult to understand? You can please ask. I can explain in detail and what part you are facing difficult, because these are very abstract mathematics. Okay. So you may find it difficult to understand or visualize. That's why this session, that is the one of the agenda of this session. Okay. So what is this operator actually? Anyone among I think there are 13 participants, 11 participants. Anyone can unmute who face difficulty in understand these operators. Okay. Or you can simply write in chat that you face difficulty. I can make it more convenient to you, else I will just solve the numerical. Mayur, right? Mayur, you have your audio on. We can have a discussion. It will be better for you to get your doubts cleared. So what part do you find difficult in this? Actually, you are not audible, Mayur. Okay, just let me explain anyway. You are not audible. So what happens actually that these all operators what we are talking about, right? These operators are basically linear differential operators. Okay. Linear, you mean, right? Homogeneity and superposition. Those two properties should be satisfied. That is what is linearity. There is no other definition of linearity apart from that. Whatever you read in signal system, same thing applies here also. Differential operator means it has to do with some differentiation. Okay, that's all. What does these operators do? Basically, say A is an operator. Okay, it operates on a function, a complex wave function. It generates a quantity times that function. This is all there is two operators. Okay, this A is your operator, linear differential operator. It acts on this psi function, creates a value alpha times the same wave function. Okay, this is your operators. Now it has some exotic names based upon who has invented and all. Okay, so this function is called eigenfunction. This value is called eigenvalue. Okay, or you may say you can replace eigen with characteristic. The same problem you study in your linear algebra course, right? In your matrices and vectors and matrices, right? The same concept applies here also for the eigenvalue thing. It all comes from your linearity. Okay, so these linear differential operators operate on your eigenfunction, creates eigenvalues multiplied by the eigenfunction. Okay, so now how does this become your kinetic energy operator? This becomes potential energy operator and this becomes energy operator. For that, let me tell you a small part. Okay, suppose your P is an operator. Okay, momentum operator. Let's say P is called a momentum operator. Okay, by the way, if you have difficulty in understanding this thing, it is nothing but your, this is your kinetic energy, this is your potential energy, and this is your total energy. Okay, Schrödinger equation is nothing but your energy conservation law, and this you can easily get from the this operator fundamentals. So if it is a momentum operator, so momentum operator works on your wave function and it creates, let's say, some eigenvalue. I am calling it as momentum multiplied by your this function. Okay, so how you can formulate what my P should be? How can you get? You assume your wave function as a plane wave solution. Okay, this form you are familiar of. This is a traveling wave in x direction. Is that okay with you? It is nothing but your cos a cos x plus I a sin x. Okay, and it has some time varying nature. Whatever we have studied in your electrodynamics and all, e to the power minus j omega t, it is the same stuff. Okay, so now say you want to uh, and by the way, what is your momentum in quantum mechanics? What is your P? P is your h by lambda, and this is from de Broglie relation. Fine. So h by 2 pi into 2 pi by lambda, I can write it in this form. What is this? This is nothing but your h bar or reduced Planck's constant. And what is this? This is nothing but your k or wave number. Okay, so your P is nothing but hk. Fine. So I need to find some operator. Let's say A is my operator, which operate I used this P, right? So P is my operator, it operates on this and it creates a function like h bar k into psi. Okay, if I can manipulate my this operator or this P operator, I am denoting with a underscore, right? Minded. So how can you get this k, right? K, how can you get k out of this? You just need to differentiate it with respect to x. Okay, so let me just differentiate with respect to x. What I will get? I k times a e raised to I k x minus omega t, that is nothing but I k times psi. Fine, d psi by dx. Okay, now let me do one thing. I want h bar k, right? So I multiply with h bar, divide by I. So this I gets cancelled. So my h bar by I d psi by dx becomes h bar k by psi. Fine. Now you take out this much and call it P underscore or operator P. So what happens? This my operator P becomes h bar by I d by dx. Okay, you understand how this formulation of these operators are coming about? Similarly, you can do for total energy operator. Total energy is your h nu or your h omega. H nu is nothing but your h bar by 2. Just let h by 2 pi into 2 pi into nu. 2 pi f or 2 pi nu is nothing but omega. So your h bar omega. Similarly, to find out omega, you need to have some ddt formulation and some constant multiplied here, from where you can find this total energy operator, right? So that's why you can formulate all the operators. It is nothing difficult once you understand what are the operators. Operators operate on eigenfunction, creates eigenvalues multiplied by the same function. Okay, so now what happens that you want to find out the kinetic energy operator. Okay, so kinetic energy, what is kinetic energy? Let's say kinetic energy operator I am writing like this, ke underscore. Okay, it is nothing but your p square by 2m, half mv square, right? Half mv square I have shown you, right? Half mv square, m multiplied by on top and bottom, denominator and denominator. M square v square becomes p square, and in denominator you have 2m. So that's how ke is equal to p square by 2m. So once p square by 2m, you know what is p, right? It is a h bar square I square into 2m, and it will be del square by del x square. So what is your I square? I square is nothing but -1. So this is your kinetic energy operator. You see, this is your kinetic energy operator. This part. How does this come about? Okay. So now may you tell me in the chat box that whether you have understand how these operators are coming, how the Schrödinger equation is getting formed and not. It is pretty easy, right? You need to just have the concept of operators and energy balance, energy conservation. That's all. Potential operator is same. This is Vx, V psi means this is how we define the operators. It is equal to V psi only. Okay. Did you get it? You are not audible actually. I do not know whether you have connected with proper audio channel. You can just chat, type in the chat box and tell me whether you have understood it or not. Okay, I guess that you have understood it. Okay. So first thing is that Schrödinger equation is not difficult. It is an energy balance equation. Okay. And you just need to understand how to deal with the operators. These are very easy because it are linear operators and differential operators. Okay. So now Schrödinger equation you know, right? Now let me go back to the problem. Let me just copy it. Okay. So now let us try to solve this. Okay. So the Schrödinger equation at region 1, this is, let's define the regions. Okay. This is region 1, this is region 2, this is region 3. For region 1 and 3, my psi is simply 0, right? Because we have already discussed that the particle cannot exist outside. So the probability will also of finding that particle outside will also be 0. So the wave function will also be 0, right? It is not the other way around that the wave function is 0. That's why the particle probability should be 0. It is that we cannot find the particle there. That's why the probability density is 0, and that's why the wave function is 0. Now let us focus on region 2. In region 2, here my V is 0. This line is V is 0. So my Schrödinger equation is equal to E psi, here this quantity will become 0 because my potential is 0 inside from x equal to 0 to x equal to L, right? So what happens? It becomes a simple equation. D square psi by dx square is equal to minus 2me by h bar square into psi. This is just a simple homogeneous differential equation. So you can easily solve it. This is your, let's say this is your k square psi. Let k square equal to 2me by h bar square. Okay. So what happens now? What is the solution of this kind of equations? This is your nothing but a sine of kx plus b cos of kx. If you are not convinced that this is the solution, what you can do? You can anytime just simply take your d square psi by dx square and check whether it is coming as equal to minus k square psi or not. Okay. This I am leaving as an assignment or some simple homework to you that you can always check, right? Similarly, suppose if this was plus, what would be my solution? The solution would be of the form of a to the power bx, or sorry, a to the power kx, right? As simple, because if you do the double derivative, it becomes one times k will come, another time k will come, and it will be kx only. So k square psi will only be remaining there. So that's how we just guess the solution of this kind of equations. Okay. So if this is the solution, now how will you find out the solution? We need to apply the boundary conditions, right? So we know from the properties that at these 2 points my wave function has to be continuous. It has to be continuous anyhow, but at these 2 points also it has to be continuous. So at psi of 0 should be 0. So if you just put this in equation A, what will you find? 0 equal to x equal to 0, this term will be 0, b cos 0, right? So your this is 1, so b is equal to 0. So now what do you get? Your psi of x becomes a sin kx only. Okay. Now your psi of L should also be 0 because at this place my wave function is 0. So at this point also my wave function has to be 0, and also at 0 L minus. Okay. So from this what you get? A sin kl equal to 0. So sin kl. So why can't your A be 0? When you are writing from this step to this step, you are assuming that your A is not equal to 0, right? Otherwise it will be simply giving a 0 over 0 for formulation, 0 by 0 formulation. That is not anyway valid, right? A cannot be 0. Why? Because if suppose A is 0 from this equation, you know that your psi x will always be 0. That is a trivial solution. That means the particle is not present even inside the potential well. That is not possible, right? Particle has to be present there. So A cannot be 0. So we can write that sin kl is equal to 0. So you know the solution, that k will be equal to simply n pi by n. What is the value of n? Can anyone tell me?
Integer values.
Why integer values? Why cannot it be 0? 0 also satisfied the solution, right? You mean to say n is 1, 2, 3 like that, right? Why can't n be 0?
N equal to 0 means it is a void state.
It
That
is a
means there is no state present. Energy state.
I am not still convinced. Can you please explain it some other way? Okay, just let me tell you same reason what I have told you for a equal to 0, right? If your n equal to 0, that means your k is always 0, right? So again, from this equation, you see that your psi x becomes 0. I think that is what Srihari has meant, that there will be no states of energy. That means the particle wave function inside the well is 0. That is not a valid case. The particle has to be there. We know that from which principle? The normalization integral, right? The very first question. So n starts from 1. So what is my ground level? This is n equal to 1 is my ground level. Okay. So these are very tricky points. Okay. This you need to be very careful about that. Why this is not the case, and whenever you just do not ever from now point onwards, do not ever, if you have any constant, just divide by 0 and it will, you assume that it is a non-zero quantity. You need to have a proper reasoning why the trivial solution is not acceptable. Okay, keep that in mind for any calculation, for in any field, whatever you do. Whenever you have some quantity multiply equal to 0, and if you have some constant multiplied to that quantity, you cannot just simply bring it down to the denominator and make it 0, the overall right hand side to be 0. That is not how it works. Okay, so if this is the case, now we invoke the normalization integral. And remember this point always, that to find out the value, what is the form we have now? We have psi x equal to a sine n pi by l into x. Okay, what is unknown? A is still unknown. Okay, remember this thing. Take it as a golden rule, though it may not work always, but most of the cases what you will be facing, it will work. Whenever you need to find out the value of amplitude of the wave function, in most cases you need to invoke the normalization integral. Okay, so what is the normalization integral? Minus infinity to infinity psi star psi dx equal to 1. So what is the limit? Because beyond this is 0, so a limit should be 0 to l, and the my psi is real quantity, right? So psi star psi is nothing but mod psi square is nothing but a square sine square n pi by l into x. Okay, so your a square sine square n pi by l into x dx equal to 1. Okay, so should I do the integration or you can solve it? It is simple, right? It is just 2 sine square, this means 1 minus cos 2n pi x by l, this dx equal to 1. So this part of the integration will be 0. So a square by 2 into l is 1. So your a is equal to root over 2 over l. Fine. So what is the solution of your root over 2 over l into sine of n pi by l into x? Okay. This is the wave function final form. And what about the energy levels? E is equal to what? E is equal to, from this place, E is equal to k square h bar square by 2m. Fine. K square h bar square by 2m. What is k? K is by n pi by l. N square pi square by l square into 2m into h bar square. Okay. So what is my E ground, or the lowest level of energy? What is that? That is when my n is minimum. And what is the minimum value of n? We found out that it is not 0, though it satisfies the equation or the condition. It is n equal to 1. Okay, so this is my ground level energy. And what is my E4? Because my question has asked, right? We started with this, that it has some energy levels. Let's say this is E4, this is E0. So an electron jumps from this to this, and in the meantime a photon gets released. Okay, so I have this formulation: E4 n equal to 4. That means it will give me, what is 4 square is 16, 16 pi square h bar square by L square into 2m. Okay, so what is the energy difference, energy lost by the electron? E4 minus Eg, that is nothing but your 15 pi square h bar square by L square into 2m. Fine. Now this energy has been released as a photon. Okay, so this energy has been released as a photon of wavelength 20.9 nanometer. Okay, so what is the energy of photon of 20.9 nanometer? E photon is equal to h nu. What is photon? Photon is nothing but electromagnetic wave, light wave. So speed of light is c. So nu I can write c by lambda. Fine. So this energy should be equal to my delta E, this energy, because this energy lost by electron has been released as a photon. So your hc by lambda is equal to 15 pi square h bar square by L square into 2m. Okay, here you know h you know, c you know, pi you know, h bar you know, m you know, lambda you know. What is lambda? 20.9 nanometer. H 6.626, 10 to the power minus 34 joule second. M 9.1, 10 raised to minus 31 kilogram. C 3 into 10 to the power 8. Okay, so all it needs to find out is L. So you can easily find out L. What is L, by the way? L is the width of the potential well. So if you calculate, you will find out that it will be your option B, or 0.308 nanometer. Okay, 0.308 into 10 raised to minus 9 meter. This you will find out if you put all these values to this equation and calculate your L. Did you get the point? Anyone have any difficulty in understanding this problem? Because this is one of the fundamental problems. If you understand this thing, future problems will be just a piece of cake. If you have any doubt, ask at this stage only.
So,
Yeah,
so this potential, this psi x formula is for infinite potential barrier.
which formula?
The
This one?
normalization. Yes, sir. The last one.
Okay, just let me tell you. Why are you concerned about the formula?
So, does it like differ for finite potential and
No,
infinite?
it will not be. It will not be the case. For finite, you cannot have. You can have waves crossing beyond the boundary, right? Similarly, what we have discussed, that if you are in a well, at the bottom of a well, and if you have a particular level to climb up, you have seen that Batman movie when the Batman has climbed out of that well, right? So it
Yes.
can be climbed out. So beyond x equal to 0 and x equal to L, you can have some wave function present.
Okay, sir.
So it is not sacrosanct, or this is not for all the cases. And please, I am requesting to all of you, do not mug up any formula, okay? I have spent time on this formulation because I know that Schrödinger equation understanding is very difficult. at the first place, but it is very simple once you have the idea of these operators and all. Just write the Schrödinger equation. Even if you do not have to remember the Schrödinger equation, right? You can start from this place. This wave equation you know, right? This you cannot forget. This wave equation you know. You just need to know that the energies are conserved. From that you find out the Schrödinger equation. Once you do 4 or 5 problems by yourself, you will automatically the Schrödinger equation be imprinted in your mind. Okay. And from thenceforth you start with this equation. And then it is just a manipulation, right? In which the first thing, whatever problem you are given, divide it into regions. Okay. And this is not for this case only. In your future, any courses, if you have a huge problem or large problem, just break it into some smaller problems. So I told you that you break it into 3 regions. Even if it's some finite potential, then also you need to break it into 3 regions and solve it region by region. Okay. Once you solve it in this region, you see that your potential is 0. Already one term will be gone. And if it has some finite region potential, so in this region you will just take it as a constant volt potential, and instead of this you will have this term going to this side and it will have some minus v kind of form. Then you can also solve it, right?
Yes.
So don't ever mug up this formula, and how don't be scared of this formula. Okay, you can easily get it derived. Just first few problems whatever you will be facing or be doing by yourself, do step by step, and then you see after 2 or 3 problems it will be automatically imprinted that how the steps are, and you can do for, believe me, you can do it for any such kind of surfaces. Even for the most difficult case of delta potential at the boundaries you can also do. Okay, so I think if you have any doubt you can already revisit the video. We'll share the recording. So next thing, a wave function is given by this kind of nature. So what is that? Again the same thing. It is some potential, well, x equal to 0, x equal to L. Beyond that it is 0, 0, and it has some nature in between. Okay, and we are asked to find out the value of A. What principle should I invoke here? Can anyone tell me?
Normalization.
Exactly, right? I have already told you. And also if you are a little bit inquisitive, you can see that to find out the value of A or the amplitude of the wave function, in most cases you have to use the normalization integral. Okay, so I will directly write it now. Okay, just let me do it again for this one particular case. This is the normalization integral. There is nothing to remember mug up about it. It is your probability density. It is your probability for a small region. It is the probability for entire region, right? Density into volume. Generally, what do we get in classical mechanics?
Mass.
Right? Mass. Similarly, suppose I get probability density into volume. It is mass density actually. Okay, the mass is silent. We do not say mass. Into volume, what do we get? Anyone? If
Existence
mass,
of a particle.
no, it is simply probability, right? Mass density into volume is mass. Probability density into volume is probability. So if this is your probability density, you just multiply it with the volume. Here the volume is a linear dimension because we are talking about 1D, right? Dx is the volume. Assume it as a volume, linear volume. So this is nothing but probability, right? For a small region dx. Now for the entire region, you need to integrate. I am just telling you how to remember or how to understand the normalization integral. Okay. So whenever you find out this kind of terms, that this kind of density, spectral density, will find out spectral density, density over what? Density over volume, density over line, density over wavelength. Then multiply that wavelength. If you get, you will get the main quantity, the fundamental quantity. Okay. Remember this thing. This will be very handy for you. So if this is my normalization integral, let me add a page. Then you see, beyond x equal to 0 and beyond x equal to L, there is no existence. So 0 to L, you have a root 30 x. Okay, I think I lost the charge here. Just give me, take a 5-minute break. Okay, I need to charge the pencil. Take a 5-minute break. Okay, I have one question from that. As we are about to complete 75% of the problem solving session, if you could touch upon query, it would be grateful. So what query did you have, Mayur? Just let me. Mayur is the one whose microphone is not working, right? Okay, please share the role of this theory in this training. Okay, in this training, what training? Uh, you can text that what kind of training you are talking about. By the way, in the meantime, when I take a 5-minute break, can you please tell me your backgrounds, that which year you are from? First year, second year, final year, PG? You can unmute and just tell me. Let's start with this. Okay. For I have been appointed as a trainee for training title Electronics Devices and Circuits. I am not getting you, Mayuk. Actually, I may be not aware of it because this is an NPTEL course, right? I am not sure what training you are talking about. This is basically taken by the undergraduate and PG students who want to enhance their understanding of the subject. Okay. So see these concepts of this quantum mechanics. If your question is that how quantum mechanics helps in understanding or how it will be helpful in your domain, let me tell you that every theory what will be developed henceforth or from now will be based upon this understanding of these concepts only. Okay. So see, you can reach to a certain level of understanding from any point of step. Okay, suppose you start from level 0. This is starting from level 0. So there is nothing beyond this quantum mechanics for you as of now. So if you start with quantum mechanics, then you go to the semiconductor devices, that how these dopings, for example, I told you this problem regarding this problem, right? This lithography thing. So you will find out that what does the lithography means and how does it help? How does quantum mechanics help? But quantum mechanics helps you to understand that what amount of energy of electron you require to make those nanoscale amount of printings. Okay, so this understanding is very necessary for you to have when you go to the industry, do the hands-on fabrication if you will do, or even it will be very satisfying to you to understand that for a nanometer printing for a on a semiconductor chip or the IC, you need to have that much of energy with 200 50 kilo electron volt, 100 kilo electron volt of energy of electron gun, right? So do the problems diligently, I would say, and also if you have time, don't only just go through the problem to solve for the numerical point of view or numerical sake, also do the backgrounds also. Okay, read every word of the problem carefully, problem statement, and try to introspect what those things mean. If you don't understand, that's why where you ask the question, myself or Atib in the previous session, you ask the questions that what are these things, because you do not get to interact with the professors of this course for an weekly basis or kind of that, right? On a live interaction will be there, but it will be very limited, 1 or 2 sessions. But we have your time for 2 hours every week. Okay, so get your doubts cleared in that. Any point of doubt, we may not be able to answer all the question at the very front from on top of our mind. Okay, but we will definitely collect the information or route you to the proper resources. That much we can do, and that will be very helpful to you. Okay, so 5 minutes is up. Let's see. Yeah, we were at this place, right? A30 x L minus x, this whole square dx should be equal to 1. Okay, so a square 30 into x square plus L square minus 2xl 0 to L dx equal to 1, a square 30, and this integration you can do, I think, or just let me do it quickly. X to the power 4 plus x square L square minus 2x cube L. Okay, I think this you can manage, right? So if you do that, you will find out that it comes out to be L raised to 5 over 30, okay, equal to 1. So this will get cancelled out, and you have a square equal to L raised to minus 5. That means your a would be equal to L raised to minus 5 over 2. Please, Tanish, please mute your microphone. Thank you. So this is your right answer. Okay. So this is pretty simple. Just we needed to invoke the normalization integral. So again, let's move to next problem. An electron is bound in an infinite 1D potential well of width this. Same problem, width we know, it means L is 7.3 nanometer. Fine. Along the axis, the system is at state n is 3. The probability of finding the electron per nanometer, probability of finding the electron per nanometer length at x equal to 3 is, so we have our psi, right? What was the psi for this case? Root over 2 over L sine of n pi by L into x, right? So what was the probability density? 2 over L sine square n pi by L into x. Okay, so what is the probability per unit length, per nanometer length? Probability per nanometer length, again, what does that mean? Probability per length means it is nothing but probability density, right? Is it clear? Let me ask Srihari, is it clear that probability density is nothing but probability per volume? So in this case, in 1D, volume is nothing but length. So probability density is only probability per unit length. So they are asking us to find out the probability density. Please tell me at this point if you do not understand.
Yes, sir.
Anyone. Okay, so they are asking us to find out the probability density only, not the probability, because probability per unit length means probability per unit per nanometer length, whatever it is the unit we can adjust later. Okay, so what you need to do is that this psi star psi is equal to 2 over 7.3 nanometer into sine square. What is n? N is 3 pi over L is 7.3 nanometer into multiplied by location is x equal to 0.3, right? 0.3 nanometer. Okay, so this units gets cancelled. So if you find out that what is your psi square psi, it will come out to be 0.039 into 10 to the power 9. Okay, but they are telling us that you need to consider per nanometer length. Okay, so if you consider per nanometer length, so this will also be gone. Okay, so probability density per nanometer length is your this. Calculate this thing. I think you can easily calculate this thing. Just don't know, when you put this pi in your computer, in your calculator or MATLAB, you just check that pi is equal to 180 degree. Okay, or because pi is in radian, just make sure that radian and degree thing you get it corrected. You will get this result easily. Okay, so this is your right answer. So let's move on to the next problem. Okay, electrons are accelerated through an electric potential V. Okay, and then fall on a pair of slits that have a separation of 100 nanometer. Okay, so this is one slit, let's say this is another slit. Slit means gap. Okay, so this distance is, they are telling that it is 100 nanometer. Fine. The resultant interference pattern, say there is a wall here and electrons are going like this, and there is a some wall where we see the electron interference pattern. It will be something like this. Okay, let's say somewhere it will be constructive interference, somewhere it will be destructive interference. So what are they telling? That through an electric potential V. Okay, so there has to be some electric potential which attracts the electron. Can you tell me what is the sign at these two places? This, let's say this is the source. If I have a battery, right, I say V means it has to be have some positive sign, some negative sign. Okay, can any one of you tell me what is this question marks? Will should I replace to, where it should be plus and where it should be minus?
Left hand side it will be negative and right hand side it will be positive.
Left hand side it will be negative and right hand side it will be positive. Is that what you are telling?
Since electrons will be repelled by negative potential, it will be attracted by the positive side.
So what is the direction of the electric field?
The conventional current direction may be from plus to minus, but the electrons will flow
No,
from
no,
minus to
right,
plus.
right. What is the direction of electric field?
Plus to minus.
Right. This is the direction of electric field. Okay. Always remember that it is not the voltage which makes the electron move, it is the electric field. The fundamental thing is electric field. Okay, so just let me tell you one thing. If you have 5 volt, okay, and if you have a distance of, let's say, d, and again another where you have a distance of 2d, and you have this same 5 volt, so electron will move here like this. Can you tell me in which case the electron will feel more attraction or more speed or velocity?
Where the distance is lesser.
Distance is lesser. Why so?
Because from the electrostatic force of attraction, the force will be inversely proportional to the distance square.
Right, right. So the other way of telling is that electric field is nothing but your potential by distance, right? So electric field is more in this case than this case. So that's why I was telling that field is the fundamental quantity which makes the electrons move. Okay. So you will from henceforth never say that for this potential electron is moving. Always say that because there is a presence of electric field, that's why the electrons are moving. Okay. So now the question is, what is the value of the, so you understand this picture, right? The first two statements, it is very important to understand the or imagine or visualize the picture as well. Okay, what the problem is telling. So what is the value of the accelerating electron potential? What is the value of the accelerating electron potential V? Okay, so potential they want us to find out this. Okay, so first thing, what is the energy, potential energy of electron? Anyone can tell me? If the potential is V and electron charge is Q, what is the potential energy? It is nothing but QV, right? And what is my kinetic energy of the electron? Is your P square by 2m, right? Same half mv square. So you see the electron has a wavelength of 1 nanometer. And why does that wavelength come into picture? Because the electron is moving or the electron has some kinetic energy. So what is your EK? Again, what equation should I use? I use the de Broglie equation, h square by lambda square into 2m. So this energy should be equal to this from the energy balance, because due to the presence of electric field or the voltage between two regions, the electron is moving from one place to another place, right? So your h square by lambda square 2m should be equal to qv. So what is your v? V should be equal to h square by lambda square into 2m into q, right? What is your h? 6.626 into 10 raised to minus 34 joule second. Remember the units very carefully. Okay, I do not have time to make you understand how the units are playing, but it is pretty easy. Just break down everything into the 4 fundamental quantity. What are those? Time, length, mass and temperature, right? If you can break the know the fundamental laws of physics, then you can correctly manipulate all the units. Okay, so h is this, lambda we have told is 1 nanometer, that means 1 into 10 to the power minus 9 meter. This is one, lambda is mentioned here. M we know that 9.11 into 10 raised to minus 31 kilogram, and Q we know what is the electron charge, 1.602 into 10 raised to minus 19 coulomb. Okay, so you can easily find out this V. If you just plug in these quantities into this relation, you will find out V to be 1.5 volt. Okay, So the first portion of the question has an answer of V equal to 1.5 volt. Okay. So let me go to the second part of the question. That is, after passing through the slits, what is the minimum spread? What is the minimum spread of the electron's momentum in the direction parallel to the plane of the slits and the perpendicular to the average of the electrons? Okay, that means in this direction, what is my delta P? Okay, that they are asking. What is the spread in momentum? That means what is the I would say you can tell it as a standard deviation maybe. For example, standard deviation is a spread, right? For a Gaussian plot, if you see the nature probability of something quantity is here and it is here, so you see this would be your standard deviation. Maybe this quantity you call it as sigma. So this is a spread. So the in quantum mechanics we define spread by, spread means basically some width of that dimension, right? Some distance. So we know that, right, from Heisenberg's uncertainty principle. What do we know? That delta P into delta X should be greater than equal to, anyone?
H bar by 2. H bar by 2.
Can you prove this? Okay, not needed at this moment. Okay, it is a very simple proof. Okay, again, whatever I have discussed today, you can just plug in the values and you can just prove it. It is as simple as that. So your just do not put the inequality sign, that needs more introspection. So you need to find out delta P, right? So that is your H bar by 2 delta X. What is your delta X? Delta X is your 100 nanometer. Okay. So you can find out your P as greater than equal to H bar by 2 delta X, or H bar equal to your what is H bar? H by 2 pi, right? It will be around your 1.05 into 10 raised to minus 34 joule second, and your delta X is 100 nanometer, that means 10 raised to minus 7 meter. Okay, so if you calculate your delta P, you will get around your 5.5 let me say 27 into 10 raised to minus 28. What is the unit?
Kilogram meter per second.
Why it is spread, right? Why should it be kilogram meter per second? Actually, you are right. It is kilogram meter per second because spread is nothing but some P2 minus P1, right? So when you do subtraction, the unit doesn't change. So the spread will also have the same unit of momentum. Okay. So the minimum P should be from this inequality sign, that 5.21 into 10 raised to minus 28. So let us go to the options. So this is not right. This is not right. This part is right. This is not right. So D will be your option. It is given double almost, right? It should not be that. Okay. So let's move on to the next problem. I think I'll do this problem as the last problem because please listen this problem carefully. Okay, look at this problem carefully. This is a very important problem. The wave function of a particle at state n is given by this. Okay, same thing, same stuff. It is your 0, it is a by 2, it is minus a by 2, and this wave function is given like root 3 cos 2 pi x over a. Okay, this is your psi. What is the average momentum of the particle at state n? How do you calculate momentum? Sorry, how do you calculate average value? Let's say average value of a. How should I calculate? This is how you calculate the average or expectation value. Weighted average you have read in your you have studied in your +2, right? How to do the weighted average. So this is just nothing but that's the same concept, extension of that with the linear differential operator. Okay. So can anyone tell me what I have done here? Just rephrase what I have written. That will be sufficient. You may not need to tell me what is the meaning in between, but just tell me whatever I have written in proper words, that this operator is working on this multiplied by this, and then it is giving me this. Okay. Anyone? I would request Bhagmita Datta. Can you please unmute and tell me? I just need to check whether you are getting these things or not. The operator part. Can you unmute and just tell me what is the right hand side? What is it happening here?
One of them is the eigenvalue is the A is the eigenvalue.
No, no, no. A is the operator.
A is the operator.
Right? Operator I have been denoting with this underscore.
Okay.
So A is the operator. It is operating on
That value after
that's
it.
psi, right? Psi. PSI, psi.
Right.
Okay? Psi. It is operating on psi, the wave function. And what will this give me? This part, only this part, what will this give me? This will give me nothing but the eigenvalue into the wave function, right?
Yes, yes.
So eigenvalue into the wave function. So now if I take this eigenvalue outside or just write it in this form, do you see this is a normalization integral apart from just alpha?
Yes, sir.
So normalization integral give me some kind of average value.
Yes,
This
sir.
alpha will give me the average value of alpha. Okay. Oh, I have written this wrong. This should be alpha. Okay. So now,
So,
yeah.
so what is the significance of average value of alpha? It's the
Oh,
eigenvalue.
yeah, right, right. Let me tell you the average. What is the significance of average value? Okay. I would say that in statistical domain, or let's say whenever you are not sure how the waveforms will be behaving at one point in space or to the other point in space, right? See, instantaneous waves, you know, instantaneous signals, random signals.
Yes, sir.
So this kind of wave function may not be deterministic. Okay, even if the wave function is deterministic, its operators or its derived values like momentum, energy may not be deterministic. It may vary from each point to other point over the space, right? So how do you deal about it? You cannot do calculation or make a sense of by looking at each point. You have to make a average sense, right?
Okay.
Suppose you are in the month of what month we are now? We are in the month of July, right? In the month of July, there are raining in all over India, some in some portion of India. Okay, for let's say, let me take Uttar Pradesh. In Uttar Pradesh, somewhat raining is there, but for each day, if you see over the July, can you tell me that on 1st of July there is this much rain? So my on 3rd of July there will be this much rain, or the season is rainy based upon the particular data of 1st July or 10th July. You cannot do that, right? You have to make a sense of the overall month,
Yes,
overall
sir.
July. That July is a rainy month because you know at an average that there will be rainfall. Okay, so in that sense, you can think of that same way that momentum may vary throughout the space, right? Because we are integrating over the space, but its average sense we need to make out. Okay.
Yes, sir.
So how do we make the momentum? So average value of momentum would be, tell me, integration
By
psi star multiplied by the, now what should I use? The momentum operator, right?
yes, sir.
So what was the momentum operator? Momentum operator was h over I del x
X, yes,
into psi.
yes,
Okay. Now psi you know, right? This quantity you can calculate. So what it will be? H over I, this to this. What is psi star? Psi star is real, right? So it will similarly be psi only. Cos 2 pi x over a. And what about the derivative of this? D psi over dx. It is nothing but root 3 into 2 pi over a into minus sine 2 pi x over a, right? So minus, it will be root 3 into 2 pi over a, and it will be sine 2 pi x over a dx. So it will be minus h bar by I. So root 3 will be 3 pi over a, and 2 sine a cos a means sine 2a. So sine 4 pi x over a dx. Okay. Now you see, this limits I have not changed. So the limit you need to change it from minus a by 2 to plus a by 2. Fine. So minus a by 2 to plus a by 2. You will get simply that, notice that it is an odd function. So what is odd function? That your sign starts from here, right? So if it is 0, it is a by 2, it is minus a by 2. If you integrate it, this negative and positive will give you always 0, right? Whichever point you take. If the point is symmetric around 0, some positive area and negative area will give you 0 area. So this will be 0. So 0 multiplied the constant will be 0. So 0 will be your right option. Okay. So this is where I will end today. Please tell me this part, this particular problem, have you understood or not?
yes, sir.
So you can now calculate, if anyone asks you to calculate the average value of energy or kinetic energy, you can do, right? What will you do for, let's say, kinetic energy average value? Same thing. This psi star, and what is my kinetic energy operator? Kinetic energy operator is minus h square by 2m del square dx square of psi. Okay, then dx. So this is the average value of kinetic energy. Okay, so in this way you can calculate your average values. Fine. I think that's all for today. If you have any
Sir,
question, please ask.
how are you writing average value?
Okay, average
Sir,
value. Yeah.
average, sir, it is integration over the time,
What the
1 by time
space?
period in, sir, 1 by time period into integration, total divided by number.
Right.
Sir,
Total divided by number. But that total
sir,
divided by number thing is coming from this probability, right? This is probability density. Remember, psi
yes, sir.
star psi.
Yes, sir.
So what is your probability generally? Probability is your particular space or the number of time, number of occurrence. Sorry, what is your probability definition? That your, how many times that event occurs by total number of sample space, right?
Yes, sir.
So you see that division by total number you are telling is taken into account in the psi star psi itself.
Yes, sir.
Okay, are you getting the feeling that how we can write this? If you don't
No, sir.
understand, please tell me. Okay, see, you must have seen some this kind of average value, right?
Yes, sir.
Okay, this you are aware of. This is just the average value of this over some time. Okay, the
Yes,
signal
sir.
over some time. Now what I am telling you, I am just taking minus t by 2 and xt by t inside and dt, and this quantity I am telling you to write it as some psi of t. Okay,
Yes, sir.
this psi of t is already normalized to the space. Okay, here the space is time, or whatever space means in whatever the integration variable.
Yes, sir.
So here you see in this form of average thing, you do not have the 1 by t thing, right?
Yes, sir.
Because normalization is already taken care of. Normalization means division by the total quantity.
Yes, sir.
So in psi star psi, already that it is already probability, right? Probability means number of occurrence divided by total number of occurrence. So
Yes,
the
sir.
normalization is already taken care of into psi star psi. Okay. So I am not explicitly dividing something here.
Yes, sir.
Now do you get it?
Yes, sir.
Okay. So anyone has any question? Otherwise we can conclude the session today. Yeah, Mayur, you are right that E equal to V by D, right, right.
Sir.
Yeah.
So
Any
we
question?
have access. Will we have access to this recording, sir?
Yeah, you will have access to the recording. Also, you will have access to the slides. Okay. Also, I cannot complete all the problems. This I will take up in next class. Okay. In the meantime, you try to complete all the assignments you have assigned to. So in that assignments also, if you have any doubt, you can just flag it out. And in the next session, you can ask. We can discuss. Okay. Okay. So let's end the session here. Okay. Thank you all. See you next week. Same time.